Well, I'm very pleased that you've come out tonight to hear a little bit about the National Ice Core Laboratory, which is at the U.S. Geological Survey in Denver. What we do there at the Ice Core Laboratory is we keep and take care of in a controlled environment and distribute and do some experiments on samples of ice that come from the presently ice-covered regions of the world. What those regions are these days is Greenland and Antarctica. When I say presently, I refer to the fact that right now we're just in a little short break period between ice cores, and for much of the past couple of million years of the Earth's history, the Earth has been covered by ice sheets of equal thickness but over much larger areas of Canada, Northern Europe, Scandinavia, and the British Isles, and some other places that aren't too well known. We've taken drill cores from each of these dots that are shown on the two maps. Oops, sorry, I went the wrong direction. On the Antarctic map, you can see big white void here. That's misleading because drilling by other countries has filled in the sampling of some of that area. This is mostly just the ice cores that we have or that have been drilled by the United States. The reason that we go and get and work on these ice cores is because by performing some measurements and experiments on them, we can get information about the Earth's past climate and the composition of the Earth's atmosphere in the past. And the reason that we do that is because we think that what has happened in the past probably has a lot to do with what could happen and may happen in the future in times when we're distinctly concerned about possible changes to the Earth's climate. Now, these two places, Greenland and Antarctica, are covered with sheets of ice that are, in many or most places, a couple of miles thick. The reason the ice is thick in these places is that, unlike other places where it snows, the ice does not melt there every year, but it stays, and one layer of ice piles up on top of another until thicknesses of about 2 miles have been reached. If you look at the cores of this ice that we drill, and some of them are about as big around as a person's leg, but they're a lot longer because they go all the way through these ice sheets, the whole 2 miles from the present surface right down to the bedrock, you can see that they're banded. What these bands are is basically annual layers of snowfall that have been compressed into ice and later thinned by flow. Here's a close-up picture. You can see there's kind of a repetition and basically two kinds of bands. Now, this slide just emphasizes that this banding, the subannual seasonal records, are preserved in the ice cores, and that they allow us to make a quite precise determination of the age of the ice that we're looking at. And by that I mean that we can just count down these layers to see how many years ago a particular layer fell. In working with records of the past, it's extremely important to know exactly what time you're talking about. And when the core condition is favorable, this allows us to do this very well. This is how we go get it in the field with a drill rig. It's a little different than an oil rig in that the motor is down the hole and supplied by a power cord and suspended from a cable. But this is how we go through the entire 2-mile thickness and bring up cores in segments that are maybe about 20 feet at a time and later cut up into more convenient lengths. That drill barrel, or part of that drilling tower, has to tilt, so we have to start in a dug slot in the surface of the ice sheet. Here it's still hard snow. It isn't really ice, but some poor guy with earplugs and a dust mask has to go down there and saw these blocks out with a chainsaw, and somebody else has to yank them up this ramp with a snow machine. Here are the drillers who've just brought up the core barrel with a little bit of the long piece of ice sticking out of the end of the barrel, ready to tilt it over and give it the opportunity to have its first examination. That's how we get out to some of the remote places on the ice, and some of them are a pretty great distance. A map of the United States would fit pretty nicely into that map of Antarctica, so you can imagine how long the distances are and how long the flights are in these rather slow C-130 Hercules that are provided to us by the 109th Air National Guard. The flights seem extra long when we have them filled up with ice core, and we tell the pilot to leave the heater off, and we have to sit back there with them. This is how we get heavy things down to Antarctica, boxes and drilling equipment and food for the McMurdo station. This is where the National Ice Core Lab is in Denver. That's just a big warehouse at the Denver Federal Center. And the Ice Core Lab was built as a separate building inside there. And there's what it looks like inside that bigger warehouse. We didn't have to pay too much attention to the structure because of that outer protection. Thick walls, a foot thick of styrofoam. And that's where the ice core is, and that's what it looks like inside the largest room, where in these 15,000 1-meter long aluminized cardboard tubes, we fill them with ice cores. And inside each ice core would be in a plastic bag to prevent sublimation or evaporation, just like the problem you have when you leave a tray of ice cores of ice cubes in the freezer for too long. The level goes down. We don't want that to happen with our ice cores, so we protect them with at least this double layer and some other controls. It's in the mid-30s below zero in here, where we keep the ice core. We need to keep it that cold because some of the gases that we measure would be able to migrate if it approached the freezing temperature, so we keep it very cold to slow down the gases so we get consistent results. Here's a man at work cutting with a bandsaw one of the ice cores here. You can see there's some breaks in here. I'm letting some of our secrets show. All the ice cores don't turn out to be quite as pretty as I showed you in the earlier pictures. Some of them have natural breaks like this, and in fact there's some zones in the ice where they tend to come up like stacks of poker chips. This is how we keep the Ice Core Lab cold. This is a row of our electrically powered refrigeration compressors. We have more than we need so that they can spell each other, or if one of them goes down, it's automatically switched over to another one which is working. Well, that was a little bit about how we get it in the field and about the physical plant where we keep it. But let me talk now about some of the things that are of scientific interest that we get from the ice cores. There are a couple of main things that we get from the ice cores, and even though it's a bit of a simplification, let me tell you a couple of these main scientific things that come out of the basic measurements of ice cores. One is, from ice cores, we can tell the composition of the Earth's atmosphere in the past at known times, including the amounts of greenhouse gases. That's one thing. And the other thing is, we can tell how hot and cold it used to be when a particular layer of ice was deposited and was at the top of the ice sheet. When you take a snowball and hold it up, it's not as heavy as if it were an ice ball, and that's because there's air in it. There is air in the spaces between the snowflakes, or really, there's a sample of that day's air in the interstices between the ice crystals there. That's an open network of air through which the air can flow and be inside there as a sample. But as a layer of snow up at the top would be buried by successive layers and get under some pressure at depth, there'd be a time when that pressure from the weight of the new snow layers would be great enough that that network would lose its openness, and all those spaces would be closed up into individual bubbles. And when that happens, that'd be a trapped sample that would be in there for us to get back no matter how deeply that layer was buried by successive snowfalls. And we can get that old-time atmosphere out of there quite easily. We just put the sample of ice in a vacuum, either smash it up or let it melt, and the air comes right out of the bubbles, and we can tell how much carbon dioxide and how much methane, these gases that may have a lot to do with the climate, were present in the atmosphere of that time. That we know the time just by counting down the number of those layers. Jumping to this business of how hot and cold it used to be, we do this by means of isotopes. And when I say isotopes in this case, I don't mean radioactive isotopes. I just mean to refer to the fact that most of the elements on the periodic table have atoms of different weights. It's the same atom, but they just weigh a little bit different. And that's technically because they have different numbers of neutrons in their nucleuses. Hydrogen and oxygen, the two elements that make up the water, that make up the ice, they have different isotopes. And if you make a molecule of water out of slightly heavy or slightly light isotopes of hydrogen and oxygen, that's going to be a heavy molecule. I think most of you have probably heard the term heavy water in terms of in reference to the nuclear industry or the course that the Germans were trying to take in the Second World War toward developing an atomic bomb. But all natural water is either a little bit heavy or a little bit light, just because of the different proportions of the isotopes of hydrogen and oxygen that are in it. And we can take samples of ice and we can measure on a mass spectrometer, we can measure the proportions of those isotopes. Now, on the surface of the ocean, which is where most of the water vapor comes from that gets into the clouds and falls to make the snow in Greenland and Antarctica, the light molecules of water jump up out of the ocean most easily because they're light and because they move faster in their vibrations at any given temperature. So the water vapor is made of lighter water in terms of the isotopic proportions than the ocean, which is left behind with its heavier water. It's when things are cool and relaxed, or we could say low entropy, slow vibrations, that these light molecules do the best job of sorting themselves out and leaving behind the heavier ocean. When it's warmer, when things are vibrating more and more energetic and there's more entropy, it's a little bit confused, and some of the heavy molecules of water hitchhike along too. So what we find is, the net result, is that snow that came out of the ocean at cool times is isotopically lighter than snow that came out at somewhat warmer times. We can tell this difference between heavy and light water in the snow just between the seasons, between the summer snow and the winter snow. We can measure it easily, and we can find bigger differences than that between warm and cool climatic eras or regimes. This connection between the temperature and measuring the isotopes is so good that we can make a plot that's really a plot of the isotopes where heavy isotopes are up, light isotopes are down, and we can call it a temperature plot. It works that well. And here I didn't even call it an isotope plot. I just went ahead and called it a temperature plot. And what this is a graph of what the temperature was in Greenland over the last 10,000 years, where this is 10,000 years ago, and this is 0 years ago, or right now. You see the temperatures are cold, and you can say, well, who cares about Greenland? This is relevant to the whole North Atlantic region because the atmosphere is so rapidly mixed, and this tells a lot about what the climate was and how stable it was over northern and western Europe, eastern United States, and Canada. So this means something. That's why we do take these samples from Greenland and Antarctica, because they're relevant to broader areas because of the way that atmosphere mixes so thoroughly and rapidly. So what's it been like for the last 10 grand? Well, you can see there's some ups, there's some downs. You can see, well, kind of low here, and there's a little dip in here, but you know, it's really pretty smooth sailing across here. And if somebody gave you a Magnum magic marker and said, draw the average line, you really wouldn't have any trouble. You could just put it right across. Then there's this guy here. He really got out of line. What this is a climatic event which was named by a climatologist with the heart of a poet. It's called the 8,200-year event. What apparently happened here was that the ancestral Great Lakes, which were much bigger, covering big areas of Manitoba, Lake Ojibwe and Agassiz, were perhaps held in by ice dams. And one afternoon, or at least it was a very sudden thing, the ice dam broke and put a tremendous sudden flood of fresh water into the North Atlantic, and thereby disrupted the ocean currents, which ordinarily bring warm water from the tropics up to make it so that you can grow sugar beets in Germany. This got interrupted for a while by that big event. For a few decades or even a few centuries, it got pretty cold. But this is the biggest thing that's happened in the last 10,000 years if you ignore most of the other wiggles. Now, I told you that these ice sheets were a couple of miles thick in these places, but I didn't tell you yet how much time they represent. That is, how many layers they really have in them. In Greenland, we've got 250,000 of these annual layers, or 250,000 years worth of interpretable climate history in the Greenland ice sheet. In Antarctica, it's longer. Until lately, we were telling people we thought it was about 400,000 years, but just lately, from some European drilling at a site called Dome Charlie, it looks like there's a record that is approaching 1,000,000 years pretty closely for much of Antarctica. They've pretty well got it established that it's 800,000 years old. So we've got a good quarter or half a million years of record, and here I'm showing you a plot of only 10,000 years. This isn't much. This is just the surface of the book. If we wanted to, we could expand this x-axis over to here, or take all of this and push it over to one side of the graph and see a longer period of time. And when we do that, here's the last chart here compressed into a little butch haircut over on the left, which is quite stable looking when you smash it all together here, even with this 8,200-year whisker. Now we go back to 100,000 years, where here's 100,000 years ago, and here's now, and here's this little warm time that we've been living in, and here's the last ice age right here in Greenland from the Greenland Ice Sheet Project Hole 2D. What you see is that in the ice age, not only was the temperature colder, but even more importantly, the climate was far less stable, far more subject to great rapid swings in the climate than anything we've seen in our historical times, which we know so much about. It's really only from the ice cores that we've found out that such a big fraction of Earth's recent time has been characterized by extremely strong and rapid swings of the climate. much greater than anything in our historical experience. This is a pattern of extremely rapid warming events and also rapid but slightly less rapid cooling events following them. Probably they're caused by the ice sheets reaching critical masses and sending huge flotillas of icebergs out into the North Atlantic and very seriously and for longer times disrupting the ocean current circulation. In here, apparently, those schemes of establishing Middle Eastern empires worked pretty well, and it may have been because it was allowed by the stability of the climate. Now, back a little bit to the question of the composition of the atmosphere. Measuring the ice, on the average at least, through an ice age, we find that the composition of the atmosphere in this ice age, and then this ice age here, and that ice age over there, following way back, going clear back a couple million years, the right number for the concentration of carbon dioxide during an ice age is 180 parts per million. It does fluctuate with these things, as the earlier question proposed, but on the average in an ice age, some variation, but it's 180. In a nice warm period, an interglacial, like where we live now, and in the one that preceded the ice age, and then the other one over here, the right number is not 180, it's 280. So in those warmer times, there was more carbon dioxide in the air. Right now, it's not 280. We have this elevated to 360 in a rapid spike, which began maybe in the 19th century, depending on what you count. And this is, of course, because of the burning of fossil fuels and biomass. This will go on for a few hundred years until we lose our ability to put more carbon dioxide in the air, and then it'll probably taper off more slowly than we shot it in a very sharp spike. It's a legitimate question. If these greenhouse gases have such an effect on the climate, and we've already got this elevated quickly from a proper 280 up to 360, why isn't it so hot? And the answer has to be that in the climate system, there are a lot of lag times between something that's a forcing or something that is a cause and the effect that it has later. One good example is that it's at lunchtime when the sun is closest to straight up in the sky, and the greatest solar energy is coming to a square meter of the land surface, but the warmest time of the afternoon comes 2, 3, even 4 hours later than that. That's a lag time. And another example, it's just before Christmas that the days are shortest and you get the least solar energy coming down to the Earth. But on the average, the coldest time of the winter isn't then, it's 6 weeks later around Groundhog Day. So that's a longer lag time. There's apparently a longer yet lag time between the rapid injection of a large concentration or mass of carbon dioxide into the atmosphere and the effect that it has on the climate. Some waggish climatologist has said that what we're doing now to our planet is the great unintended geophysical experiment. Maybe in a few decades we'll find out more about what this particular lag time is for this kind of systematics. On this plot, I apologize, but the person who drew it got time running the wrong direction compared to the last two. So on this one, over here is now, and here is 400,000 years ago. Several ice ages, about 4 of them. The point of this plot is that the amount of greenhouse gases in the air, in this case carbon dioxide, has very closely tracked the temperature of the Earth's climate regime through 4 ice ages. When there's an ice age, the greenhouse gases are low. when there's an interglacial, like where we live now, the greenhouse gases are higher. It's a little bit too simplistic to say whether one is a chicken or an egg, because there are elaborate feedback systems between greenhouse gases and cooling. In a way, when it gets cool, it causes more greenhouse gases to be drawn out of the atmosphere. So that's what we call a feedback reaction, a positive feedback reaction that makes things get colder. But when things get warmer, they tend to put more greenhouse gases into the air. One of the reasons that carbon dioxide is drawn out of the atmosphere in an ice age when it's cold is that all gases, especially carbon dioxide, are more soluble in a cool ocean. Then again, it's believed that the ocean was more biologically active and fertile during an ice age, and that the organisms that grew in it needed carbon dioxide to make their carbonate shells, and they were a pump that drew carbon dioxide out of the atmosphere. So that's one of the mechanisms. Then if you can break loose from an ice age, you can put carbon dioxide back in. I've been talking about climate here and the composition of the atmosphere. So it's a little bit of a misfortune for you to have me talking to you about climate, because I'm not much of a climatologist. My own field has been the trace elements that fall out of the atmosphere with pollution and dust. And I'd like to just mention a couple of other things other than climate studies that we can use ice cores for and get information from them. One example, ice cores are a great way to look for trace elements and dusts that are deposited by the atmosphere. If you try to look out in your garden to see how much things have been falling out of the sky, it's really hard to sort out because it's mixed with dirty dirt. But in the ice sheets, it's just mixed with the purest water, and you can tell when even small amounts of things have fallen out of the atmosphere and remain preserved as they're further buried by these layers. The reason that you might want to do this with pollution of heavy trace metals like cadmium and lead and silver are that it gives us the natural or pre-industrial abundances of the way the world operated in its natural state, so we can compare that to what the current situation is in our modern, industrialized, perhaps disturbed conditions. The findings from some of this work so far is that in pre-industrial times, stewing volcanoes, I use the term quiescent degassing of volcanoes, was the way that the major fraction of the atmospheric load of some fairly nasty trace metals got up, was carried around the Earth and deposited to the surface, and maybe controlled our pre-industrial poisonous trace metal environment in which people and plants and animals evolved. So I think that in the old days, the source of nasty trace metals in the air was from volcanoes. It wasn't from dust. It wasn't from sea salt. And it's been possible to sort some of these things out by making careful measurements on the ice. Even with this nasty stuff that's falling out of it, usually this glacier water is easily clean enough to drink, but you can measure the small amounts of these things due to the purity of the water in the matrix and the contrast between the small amounts of impurities and the large amounts of pure water. Another example related to the first is maybe we can tell when pollution first arrived in Antarctica as a gauge to when pollution was getting to be a strong issue on the Earth. When did industrial pollution show up? The tentative finding, and it's based on the isotopic proportions of the metal lead, indicate that pollution first showed up strongly in Antarctica in the 19th century, maybe from Australia, because they got started mining there then. But the problem's not solved, and there's some intriguing indications that there were occasional puffs, and when I say puffs, I mean occasional thin time strata in the ice that showed that lead and pollution materials with the same isotopic composition appeared occasionally as much as 3 centuries before that. Well, back just a little bit to this business about carbon dioxide, the greenhouse gases. In several decades or a couple of centuries, we're going to lose our ability to put so much carbon dioxide into the air because of running out of fossil fuels. And what's going to happen to that carbon dioxide is that slowly, more slowly than we put it up, it's going to be reabsorbed first to the standing crops of plants, a little bit more slowly to the organic matter in the soils, and a little bit more slowly, but in very large amounts, into the surface layers of the ocean, and very, very eventually into the deeper ocean, and even into the limestone rocks that constitute these huge reservoirs of carbon on this particular planet that we live on. A lot of you may have heard that there's a place in Antarctica where there's a big lake under the ice, between the bottom of the ice sheet and the underlying rock. This is called Lake Vostok. It's really about a third the volume of Lake Superior. It may have been isolated from the rest of the Earth's biological communities for 30 million years. There's a great deal of interest in finding out what the biological records in this body of liquid water may be under there. We won't find that out from the new West Antarctic core, but all of these biological questions, in addition to the chemical and physical questions that we've addressed before, are really becoming of much greater interest, and I think this is probably one of the big directions for ice core science to go in the near future. We think ice cores are great as a record, sometimes a unique record, of the Earth's past climate and environment and atmosphere, but they're not the only record that we have. There are several others. Perhaps you've heard of them. They're tree rings. They don't give such broad area information, but they give it in great detail and with great countable precision. It's very valuable. Corals, they have rings like trees. They can be used to give a lot of information rather than the information about the atmosphere and the climate of the Earth. They tend to give information about the temperature and chemistry of the oceans, which is related to the atmosphere and can be a great complementary help. There's a lot of mud on the bottom of the oceans in some lakes. The records there dwarf the time records that we have in ice cores. The records of seafloor sediments go back 50 million years, much farther than the ice cores. It's from those sediments that we know that this regime of ice age with a little break and then another ice age has gone on for about 2.5 million years. Before that, the Earth was a different place without these ice house conditions that we're really in right now. What geologists call the Spelean realm, which means caves, there are stalactites and stalagmites. These have layers in them too, which give long, well-dated records of the climate regime using information about the groundwater from which those carbonate forms were created. And in the western United States, there are things called pack rat middens, where one species of rodent has lived in a single cave for thousands of years and built up big piles with strata of things like twigs and seed husks. Inadvertently, those animals have brought in pollen from the surrounding area, which show what kind of plants did grow and could grow in the climate regime of a small surrounding area. When we use all these different kinds of records together with the ice cores, they all become more powerful and give complementary information, and it's an indication of the great complexity of the field of finding out about the Earth's past environment.